So the simplex method, which is an algorithm to solve a linear program, we'll do it in 4 parts. So we'll do derivation part 1, where we'll initialize the algorithm. What do I mean by initialization? Now the 5 conditions which are necessary and sufficient for a LP you all remember. So we'll try to satisfy those, and then you will realize that one condition is very difficult to satisfy. So that is the initialization part. Then we'll iterate in the algorithm. When you say iterate, which means that we'll go from one vertex to the other, which I just mentioned, and try to satisfy it. Then this algorithm doesn't always work. That is why I was saying do the interior point method. So there are certain cases when it fails. So those we'll study separately. There are 3 failure cases. And then what is the most difficult part is starting the algorithm. Starting in the sense priming it or finding where to begin. So all this will make sense once I explain this. So what will happen, this we'll do today, and these will take the next lecture. This will now happen after Diwali. So they will take probably 2 lectures, or I may finish this in 2 lectures together. I don't know how much time this will take. But this is what will happen. Once we finish this, then we'll start the quadratic program. And that's the only till quadratic program is in your syllabus. So that is what we'll see. After Diwali, we'll have 4 lectures. So we'll see how much we can do. But nevertheless, so I'm starting the very first thing, derivation, initialization part. So like I said in the introduction to LP, the feasible region AX equal to B and X greater than 0 forms something called as a feasible polytope. So in 2 dimensions polygon, 3 dimensional polyhedron, 4 dimensional polychrome and so on and so forth. Another observation is solution of an LP lies on the, what's the spelling of lies? L-I or L-Y? Lies will be? Let's just write in. Solution of LP is on the vertices of the feasible polytope. And then there's something called as a basic feasible point, which we'll define. So this is what I showed you at the start of the class, the 3 answers which I've uploaded in the supporting material. Geometrically, you can prove that Ax equal to B and X equal to 0 forms a feasible polytope. Geometrically also, you can prove that the solution of the LP will lie on the vertex of this. The proofs I'm keeping it out of syllabus, that's why I uploaded them in the supporting material part. Now the last part is, since we know that the feasible region is a feasible polytope, solution is on a vertex, we need to have a handle to this vertex. Handle in the sense, analytically, how do I write it down a vertex? So analytically, a vertex is written as something called as a basic feasible point. Now I'm going to define this BFP for you. So we say a point is a basic feasible point if, well, it's an if and only if, because definitions by nature are both directional. If you satisfy this or satisfy that, it's a definition. If, first of all, it is feasible, so we'll say a point X is a basic feasible point if and only if it is feasible. When we say it is feasible, which means that it should satisfy Ax equal to B and X greater than or equal to 0. This is trivial to write. This is obvious that it should be feasible. Means it's somewhere inside or on the boundary of the region. Now we have to get the handle to the boundary and the vertex specifically. So that part is, there exists there exists a subset B with beta or B with an accent of index set 1 to n such that So we're working on this basic feasible point. If beta contains R indices, let me write it down, then it will make more sense. If I does not belong to B, which implies xi is equal to 0, we'll write something more, and R cross R matrix B is equal to A, I belonging to B is non-singular. Okay, let's try to understand this better. So in the previous example just we did, how many indices of x we had? 2. Everybody agrees there was x1 and x2. So we are looking at those indices here, we are playing with that. So it says there exists a subset B with an accent of the index set 1 to n. So recall the previous example, if there were n was 2, it will be just 1 and 2. It should be a subset such that the B contains R indices. What was R in the previous problem? 1, right? It was 1 equality constraint. So this is saying the number of equality constraints. You have to find an index set such that it contains R indices. The second thing it says, if the index set does not belong to B, then the complement of that should be 0. Which means that if I have to write this set beta complement as 1, 2, n, and you subtract beta from this, which I call this as the n set, contains active constraints. Okay, so in the previous example, for example, I say beta should contain R indices, which means that beta can contain either x1 or x2. It can either contain the 1 index or the 2 index, because there were only 2 indices, right? Now, so that is easy to satisfy. You can find an index set out of the 2 which contains 2 index. Now the more tricky part is if the I belongs to beta, if I does not belong to beta, then xi is 0, which means that if you're putting x1, let's say you say B is equal contains 1 and your n contains 2. So you should force that x2 should be equal to 0. The complement, if the index set is not in B, in this case if the 2 is not in B, then x2 is equal to 0. It can, so basically beta contains inactive constraint you can think of, and n constraints active constraints. You're separating the two. The last thing what it is saying is that the B matrix, which is formed from taking the A matrix and the column of A where the index is in the B set, that should be non-singular. So in the previous example, what was A? It was 1, 1. And if you have to take the I set, I is 1 for us. I have taken as an example, I is 1. So that will be just this guy. Is this non-singular? Yes, it's non-singular. So in that sense, that becomes a basic feasible point. So which means it's signifying geometrically the vertex of the feasible region. Is it making sense? So to find this is a very tricky task. That is why at the end I had written starting simplex. If you remember, this problem was just 2-dimensional, so you can easily play around and figure out what will be the beta, what will be the n, or the B with an accent, or n with an accent, or what will be the B matrix. When the dimension is really large, you can't actually figure out what to do with what. So it is very difficult. That's why starting simplex is another challenge. Makes sense? It will get more and more clearer as we go. So the idea which is just there to repeat that a point is a basic feasible point or a vertex of the polytope where the solution we know lies. If it is feasible, if it is satisfying this, and there exists a subset of the index set 1 through n. These are the number of x1s you have, no? x1 to xn. You can think of that way. Such that B contains R indices, that means it contains the number of equality constraints. If the index is not in the B set or it's in the complement of that, then it should be active. So B contains the inactive constraints, N constraint active, and the matrix which is formed by taking the columns from the B set, that is non-singular. So if these three are satisfying, then analytically you have mapped the vertex to a vertex to analytically you found how to get a handle to the vertex. That okay? All right. So we'll now work on this. Okay. So what we'll do is, so we're still in the initialization part. I told you three conditions: that feasible region is a feasible polytope. I told you that vertex, the solution lies on a vertex, and then I told you the vertex is defined by a basic feasible point. So those are the three things I told you. Now what we'll do, we'll apply the KKT conditions, or the necessary and sufficient. I'll let you not call them KKT. Necessary and sufficient condition. So what were the necessary and sufficient conditions? Ax equal to b, x greater than equal to 0, c is equal to A transpose lambda plus mu, b was mu I xi equal to 0, and e, we'll be calling this as j, so we'll stick to day, mu j is greater than equal to 0. So we'll now take this basic feasible point. So now I'm giving you this basic feasible point, and I want you to see whether the conditions are satisfied or not. So I'm given giving you this index set B with an accent. So now what we'll do is we'll split all the variables, the n-dimensional variable, what all is n-dimensional here? What all is n-dimensional here? X and C is a constant. Well, C is a constant, lambda, mu and X are variables. B is a constant. But what all is n-dimensional? What is r-dimensional here? That's what I'm asking. The vectors here. X is n-dimensional, B is r-dimensional, C is n-dimensional, lambda is, all this you remember, no? This is r-dimensional, and mu is n-dimensional. So we'll take the n-dimensional variables and split them into the B set and the N set. That is what we'll do. So we'll write that down first. You'll see in a minute why we are doing it. So we'll say xb is equal to xi, I belonging to this B, and xn is equal to xi, I belonging to this n with an accent. Then we'll also do the same thing for mu b, cb, mu n and cn. We'll split the variables. So let's say in the problem which we had r is equal to 3, The earlier problem was too easy. So let's say I give you R is 3, N is equal to 5, and I give you, this is my B index set and this is my N index set, let's say. So what will be my XB? X1, X3, X5, and Xn would be X2, X4. Similarly, you can write mu B as mu1, mu3, mu5, and so on and so forth. You can write all of them. Everybody okay? Yes or no? I've written this as a box bracket, although I'm putting them in a row format. Each of them is a scalar. X is an n-dimensional vector, and taking components of that which are corresponding from the B set and corresponding from the N set. Everybody with me? CB would be C1, C3 and C5, and Cn will be C2 and C4. Sorry? C is coming from the objective function, no? C transpose X. I've removed the objective function. Why are we doing it will be clear to you in just a second. Today it will be clearer. So I should have let it written. I erased it. Subject to Ax equal to B and x greater than equal to 0. X is belonging to n-dimensional and A is R cross N with R less than N. That is your problem. So now what we do is we try to satisfy these conditions 1, 2, 3, 4, 5 with given my a beta set which is given to me. I'll see what is known to me in this and what is not known to me, and then try to solve for it. Why? Because I've been given an x. If that x satisfies all of these, then I'm done, right? I found a solution. Okay. So we'll start with the A condition. So this is Ax equal to B. So let's say to this example, I again write this example. Let's say this is A1, A2 till A5, X1 till X5 is equal to B. For the example I have taken, R is equal to 3 and N is equal to 5. So what is this? This is A1 X1 till A5 X5 is equal to B. These are columns of the A matrix I have written. Usually I write the row matrices. This time I am writing the columns of the matrix. If I write this as A1 X1 plus A3 X3, although ideally I should write the X in front because scalar is usually in front, then the vector is usually later. A5 X5 plus A2 X2 plus A4 X4 is equal to B. Can I write it? I've just rearranged the variables. What is this? Correct. I'm showing this for the first time, not show it again. A2, A4, X2, X4. Everybody with me? Yes or no? What is this matrix? The B matrix. Recall the basic feasible point. The columns corresponding to the B index set, they form the B matrix. I don't know whether it's non-singular or not, but I'm just writing it. What is this? What is this? the corresponding n matrix, because it's coming from the n index set. What is this? Xn equal to B. So far so good. What did I tell you? That I'm giving you a basic feasible point, which means that I'm giving you that it's satisfied Ax equal to B, x greater than 0, and the B index set is such that it contains R indices. The complement of that contains active constraint, and the B matrix is non-singular. Those three things I'm giving you. So what do I know here? 0, x2 and x4 have to be 0 because it's a basic feasible point. The complement is that. What we also know is this is non-singular because that's given to me. Correct? B contains R indices, complement of B is contains active constraint, and the B matrix formed from the columns of taking the B index set is non-singular. So which implies that XB is B inverse times B. Is this greater than or equal to 0? Well, for the moment, let's say, okay, greater than 0. Why it is greater than 0? Because it is a feasible point, no? The very first thing I said for a basic feasible point is that it should be feasible, which means that Ax equal to B should be true, which we are trying to satisfy, and x should be greater than or equal to 0. If xn is equal to 0, xb has to be greater than or equal to 0. So for the moment I was differentiating that the B contains inactive and N contains active. So you can think of it that way also, that ideally it will be greater than or equal to 0, but to make it things easier for you, B can actually contains active constraints too. It is not mandatory. If you look at the definition, it only says the complement of B contains active. It doesn't say that I cannot contain active. I can contain both active and inactive. My complement can only contain active constraint. Everybody with me? So what did we satisfy? We satisfied A, and we ended up satisfying B as well with this, and we got a solution that XB is this. Now let's work the other conditions out. I'll leave this on the board. I'll switch to this side so that you can remember these conditions. Let's look at the C condition. The C condition is C is equal to A transpose lambda plus mu. Any doubt, guys? No doubt? Okay. So again, with the example I had taken, this would be, Nisha, tell me what should I write with the example. This will be C1, C2, C3, C4, C5. Correct? I'm trying to separate it into the B component and the N component. That is what I'm trying to do. Why? Because I know something about the N component, which I'm trying to use here. So this is A1, A2, A5 transpose. What is lambda, Misha? How many lambdas do we have in the example we were taking? Three plus mu1, mu2 till mu5. Correct? Everybody with me? So I'll write this further. So this is C1 through C5. If I have to write this as a column row vector, I will write this as A1 transpose till A5 transpose times lambda 1 through lambda 3 is plus mu1 through mu5. Can I write this? I've just transposed this. So which means that C1 is equal to what? A1 transpose times what? lambda. There will be 3 columns here. A1 will have 1, 2, 3, which will multiply with lambda 1, lambda 2, lambda 3 plus mu 1, and similarly you can write C5 is equal to A5 transpose lambda plus mu 5. Correct? So if I have to split this into CB, so I will take C1, C3, C5, that will be corresponding to the B index set. C2 and C4, that will correspond to the N index set. Yes or no? So how can I write this? So I will write C1, C3, C5 is equal to A1 transpose lambda, A3 transpose lambda, A5 transpose lambda, or I can pull the lambda out, plus mu1, mu3, mu5, and similarly you can write C2, C4 is equal to A2, A4 transpose lambda plus mu2, mu4. Correct? There's nothing wrong. Those were the rows I had taken, 1, 3, 5 and 2 and 4. So which means that this is equivalent to, what is this? CB. What is this? This is B transpose times lambda plus mu B, and this thing is Cn is N transpose lambda plus mu N. Correct? So we were able to satisfy this. Abhi we are not done with it. Now we go to this guy, mu j and xj. So you got mu1 x1 equal to 0, mu2 x2 equal to 0, mu3, mu4, mu5, all of them have to be equal to 0. If you look at the n set, what do you know about x2 and x4? They are already equal to 0, so mu can be anything, I don't know. But when you look at the B set, we have a choice, we have a degree of freedom. We are assuming that xb is greater than equal to 0. Remember the B condition which we satisfied? So we want to force the mu B equal to 0. So we will force mu B equal to 0 so that xb mu B equal to 0. This we know is greater than equal to 0, or if it's easy to remember inactive, you can just say greater than equal to 0. And xn mu n would anyways be equal to 0 because this is equal to 0. Is it making sense? I satisfied the B condition. I'm going to take this mu B and substitute into this. Is that okay? I'm still keeping this here. So once I take from B and substitute into the C coming, so I'll get CB is equal to, so let's keep the earlier, when we applied A and B, we got that XB is equal to B transpose. What did we get? XB is B inverse B, and we got Xn is equal to 0. This is what the active constraints. When we came to the C condition and we take the C and D, we take this mu B equal to 0, we'll get that lambda is equal to B minus transpose CB. Put this equal to 0, take this to the other side. Correct? And then also we will get that we already forced that mu B is equal to 0. This we had already forced, so we're not changing. Now we need mu n. Mu n, if we put lambda here, which we have got, we'll get the mu n from this equation. Yes or no? So mu n is Cn minus n transpose lambda, which is B minus transpose Cb. Correct? Did we solve for all the variables? How many variables do we have? We had the x's, xb, xn. We had the lambdas and we had the mu b and mu n. Those were the only variables when we transformed the problem. Correct? So we were able to satisfy A and B. We got that. When we came to C and D, we got these. So are we done? We have not seen at the E condition. So now we are stuck. So mu b we have forced equal to 0, but we have no idea what this mu n is. This mu n can be 0, it can be negative, it can be positive, it can be anything. If we get lucky that all the mu's n's are greater than equal to 0, then we are done. Which means the basic feasible point which I gave you is the solution of the problem. Correct? Otherwise, it is just one vertex and it is not the minima. Now you have to go to another vertex and iterate until you are able to satisfy this for all mu's. Is it making sense? Yeah. So what I am trying to say is we started, I gave you a basic feasible point. How to start is for the next 2-3 lectures, forget about it. I'll tell you how to start, how to get this B index set. How to start is to get a vertex of the feasible region. That is your goal. The vertex of the feasible region is given by a basic feasible point. A basic feasible point analytically has 5 characterizations. What are the 5 characterizations? The first characterization is that it should be feasible. Feasible meaning Ax equal to B, x greater than equal to 0. The basic characterization which they have termed it, there should be an index set B which contains R indices. R is the number of equality constraint. The complement of that should contain only active constraint. And when you pick the columns of the A matrix corresponding to this B index set, that should be non-singular. If you're satisfying these 5 things, then you have identified the vertex of the feasible region. Now we have to check whether this vertex is a minima or not a minima. To do that, we'll have to satisfy the 5 things. So what we did, we split the x, c and mu into b and n components because those were containing n items. So we split them into b and n. Once we did that, we started satisfying Ax equal to b. Once we satisfied Ax equal to b, we wrote it as bxb plus nxn equal to b. Xn is known to be 0 because you know it is a basic feasible point. The complement contains active constraint. So xb came out to be b inverse times b. Correct? Then is this greater than equal to 0? Yes, because we know that it's a feasible point, so it is given to me. Then we came to the C and D condition. So to take the C condition, we split it into 2 parts with CB and CN. When we look at CB and CN and then we look at the D condition, we have a degree of freedom in deciding what mu B would be. Because this is nothing but mu B xb and mu n xn. They should be in product equal to 0. Xn is equal to 0, so mu n can be anything. But xb is greater than equal to 0, so we force the mu b to be equal to 0. Once we force the mu b equal to 0, we get lambda straight away. Once we get lambda straight away, we put it into Cn equation and we get mu n straight away. Now we were able to satisfy AB together, CD together. Now we are only left with the E condition. When we go about and check, the mu b's are 0. If all mu n's turn out to be non-negative, greater than or equal, then you're done. The given vertex or the basic feasible point was the minima. If it is not, you have to iterate. You have to go from one vertex to the next and next and next. From one basic feasible point to the next basic to the next basic, unless you can find the minimum. That's the iteration part, which in itself is difficult to understand, which I'll not do it today. But I want you to at least understand initializing this. Makes sense? Why a basic feasible point maps to a vertex? So like the 3 questions which I said in the very early, go home and see the supporting material. read why the LP forms a feasible polytope, right? Why the solution of a LP lies on a vertex, read that. Why analytically the vertex maps to a basic feasible point, all that you can read. If I start to cover that, it will take 10 lectures to explain simplex. That's why I keep that as a reading exercise and start where you can get a handle of. Make sense? So we'll do one problem on initializing itself. In the lab also today, I've just put in the part of initializing the LP that you code it up. Very simple. I'm not asking you to iterate unless I teach you iterate, which will take another 45 minutes to do, which we'll do it later. Then you can code the whole thing up, given a starting point, given a starting vertex. Everybody clear? I repeated the whole thing again for you. If you have any doubts, you can stop me after class also. But let's do one example now. Okay? All right. So we now you doing the second part. We did the initialization. Okay, once we do this problem, it will be more clearer. The problem with simplex is it gets clearer, and the more we work on it, the more classes you'll do and do it in the lab and tutorial, it will get more and more clearer. Okay, so this is the problem to you, given to you. And so let's just write it in the standard form. So C transpose X is what is C? My back is hurting, I don't know why. Minus 4 and 0 and 0. There are 4 elements, hai na? So just keep that in mind. So it's x1, x2, x3, x4. What is your Ax equal to B? What is your A matrix? 1, 1, 1, 0. What's the other one? 2, half, 0, 1. Okay, so now if you're given this LP, you would have no idea how to figure out how many indices are there. 4. What's your name? Aditi. Yeah, wake up. What's your name? Sanjana. So you had written an email to me. Yeah? Got sorted? You going home or something? Achha, okay. All right. So yeah. So there are 4 indices. Now you have to pick the B set should contain how many indices? R is 2, N is 4. To find a basic feasible point, the beta which satisfies everything for you, not beta, it's a B with an accent I'm calling it. How many indices should it contain? 2, right? It should contain R indices. So you will have no idea which 2 to pick. You can pick x1, x4, you can pick x2, x4. You will have no idea which one to pick, and it satisfies so many things. Ax equal to b, x greater than 0. Chalo, finding 2 indices is easy. It contains R indices. The complement of that contains active constituent. That's also easy to do. You can force it. But how to figure out will the B columns be non-singular or not? So it's a difficult exercise. So that's why I said starting is a difficult exercise. So it's difficult to do, but I'll give you this. So I'll say it's 3, 4. I give you the 2 indices, which means it's a basic feasible point satisfying the 5 things, which means that the n set is 1, 2. Now let's write down what all we had solved. What all we had solved? With A and B, we had said that XB is B transpose B, Xn is equal to 0, lambda is equal to something, mu B is equal to 0, mu N is equal to, tell me what was this?
B inverse transpose.
B inverse transpose CB, and this was Cn minus N transpose B inverse times CB or lambda.
So B equal to in X.
B inverse
XB.
B in B inverse transpose CB, and this was
Xn equal to
Cn minus N transpose. ठीक है, अभी कुछ गलत नहीं है ना, यही लिखा था. So now let's try to satisfy all of this. So your XB would, first of all, let's see what is B, what is N, what is CB, and what is CN. Sorry?
Xn equal.
I'm too tired, sorry. I don't know why. I didn't sleep well, probably. Okay, so what is CB? The B index set is 3, 4. So this is Cn. This is CB in a column format, hai na? This is transpose of that. You can think of this. When you're writing it in a row format, it's the transpose. What is A? What is the B matrix and what is the N matrix? What is B? It's 3, 4. So it's the third and the fourth column of the A matrix. So this is your B matrix. This is your N matrix. Anything else we had to find? XB and XN was easy. Mu B and mu N we don't know. XS, so we can't write anything about. So we figured out these things which are given to us. What's your name? Huh? Sanjeev or Sanjeet? Sanjeet. Are you with me? Are you following the class? Okay, so now let's put, what is XB now? B inverse is? What is B? Identity matrix. B inverse is identity matrix, which means it will just be B. 5, 8. What is Xn? 0, 0. If you want to remember, this could be X1 and X2. I'm not writing, you know this. N is given to be 1, 2, B is given to be 3, 4. What is lambda? B inverse transpose is identity, is just CB. What is CB? 0, 0. Correct? Everybody with me? What is mu B? Because that's given. We force that to be 0, so we're not doing anything. What is mu N? It is Cn minus N transpose lambda. This was lambda, right? Lambda is 0. So that term vanishes. It's just Cn. What is Cn? Minus 4 and minus 2. So you got unlucky. Both your new component turned out to be negative. You wanted them to be greater than equal to 0. So now you have to do something about it. Is that okay? So just go home and revise this. I would say please read my supporting material so that you are clear why feasible region is a feasible polytope, why the solution of LP lies on a vertex of the feasible top, and why a basic feasible point is equivalent to the vertex. Even if you don't want to read that, at least remember what is a basic feasible point analytically, the 5 things, because rest of the 2-3 lectures until I finish this, I'll assume that you know basic feasible point, just playing around with basic feasible point. Now what will the algorithm do to iterate, to go from one vertex to the other vertex? So what it will say is take one index out of the B set, out of the N set. N contains all active constraints. So which means all the xn's are 0, which means in this case x1 and x2 both are equal to 0. So what it say, it pull one or two out, either of them, will tell you which one to pick, make that greater than equal to 0. So let's say in the next iteration I make x1 plus to be greater than 0. Now what will happen, why I am doing this is another story, I'll tell you. Once I make this greater than 0, this index set, index value 1 can no longer be in the N set. Why? Because it contains active constraints. If I want it to be remaining as a basic feasible point, if I want to go from one vertex to the other, I'll have to kick this out of the N set and move it to the B set. If I move it to the B set, I'll have to kick one out of there to this set. Why? Because B can only contain R indices. Again, basic feasible point story. So this swapping will start happening. You'll kick one out of here, kick one out of there, and repeat. And you have to ensure that one you sent out into this becomes equal to 0 because it is active, and the one which goes here is greater than equal to 0. And at the same time you have to ensure that you don't leave the vertex completely. So that's the iteration part, which I'll tell you once all this is digested with you. Is that okay? So in the lab what we'll do is you just code this little part up. It's very simple to code. The algorithm, the iteration is also not too long. Iteration is also 5 lines. Like initialization is 3 lines, iteration is 5 lines. But the theory behind is complicated. So you code this up, play around a little bit, and then I'll come with you only. We'll go over the papers. Yeah? So who all is doing LPs here? Can you raise your hand? 1, 2. Can you email? Did you upload your papers? We didn't give you an option to upload the paper in the proposal. Did you upload it? So can the 3 groups which raised the hand, can you email the papers to me?
We had already emailed.
I just email it again. I removed that email. Abhi jaake just email me so that I'll open those papers and I'll slowly go over the contents of the paper, where you'll see practically how LP is playing a role. In their work, actually, there's not much to go over because the focus is on a financial problem, how they're formulating it as an LP. I wanted to have a paper where there's more algorithmic emphasis. That's why I'm asking them to do interior point method. In your problem, what is the algorithm? LP, who raised hand? So anyway, send me. We'll go over in the class and give you more idea. Otherwise, you can keep working on the project. You know? Somehow you thought that the lab is mandatory. There's no mandatory in my course. It should be for fun. It should be for learning. But doesn't mean that you come, mark the attendance and hum ja rahe hain. So don't do that.